Hello. This is Concrete Path. Today, this lecture is going to be delivered to understand the concept is, say, we have to find the deflections, slope and deflection using the energy principles. So that we have the concept that deflections using energy principle. That first one is that the conservation of energy. When we say the energy is conserved, conservation of energy, we say that the external work done, on the body, on the beam, on the structure, the external work done on the body is 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 we say that 100% transferred is transformed into internal. We call it as that as strain energy, internal strain energy, that is stored strain energy. That strain energy is developed when the body gets deformed. So you have external work done, it gets converted to internal strain energy. So we write that your external work done is equals to internal strain energy developed. So we say that 100% energy is getting converted into strain energy. So we say that what's your external work done? What's your external work done? External work done. External energy or external work done. We say if you have a beam or a bar hanging and you apply a force P, so it gets deformed up to a delta. But you apply load, such that it is value is from 0 to P in some time t. So it's a gradual load. Gradually low. You apply the load gradually. Similarly, the deformation, initially the deformation was 0, so then it reaches to some x value, then after that it goes to delta. So we say your deformation delta is such that it goes from 0 to some delta. It's also gradually. And we know that strength of material, we know that there should be a linear elastic response. There should be a linear elastic material response. For that, we say that P should be proportional to the displacement produced or deformation produced. So if we plot a graph, say this one, we have that this is your deformation. So we write that here is some delta. Delta is your maximum value, and here is some P value that's maximum. So we say that is a linear relation between the two. So if we go at any x from 0 to any x, there is some value of that load required, that's px. So similarly we can say that the strain energy stored in at any time t, the stored or we can say the external work done, the small external work done in deforming the material, from in deforming the material for say small dx. For small dx, we can write that in deforming the material for small dx, we can write that equals to that area of the curve. We can say that px and dx. So there is some load, it deforms some load, that deformation deforms the material by some amount of dx. So if we say what is the total external work done, we can say integrated. So if you integrate it from 0 to that maximum load of P, that's your total P. So we can write 0 to P, and actually 0 to P naught. We are deforming the material from 0 to delta. We are deforming the material from 0 to delta because your x is in the function that dx. So we write 0 to delta, and we write here 0 to some maximum value of external work done. So we can say your external work done equals to 0 to P. What is the value of Px? Px equals to load at any x. We can write load at any x. Load at any x. Px equals to maximum load at delta. So we write at any x. Px by delta. Px by delta. Px by delta and dx integral 0 to delta. So we get the Px square by 2 delta 0 to delta. So we get the value that external work done equals to P delta by 2, 1 by 2 of P into delta. On similar grounds, we can say that for the moment, if you are applying the moment gradually 0 to m, and it deforms the material from 0 to some theta. So similarly, we can write that external work done because of that moment developed, we can write that equals to 1 by 2 of m into theta. Similarly, we can go for now internal strain energy. Now we say that there is some external work done. It has to get converted into internal strain energy. U internal. Say the same bar you had initially, we applied the load. It gets deformed by some amount of delta. So we write that we have that strength of material Hooke's law, strain proportional to that stress proportional to strain, stress proportional to strain. Then we write that your area cross section is that this one. So we write that stress equals to P by A. That equals to Young's modulus of elasticity into your deformation for length of L. So we got this one, and similarly we write that we have from the energy conservation principle, we write that U internal equals to W external. So your W external equals to 1 by 2 of P into delta. So you write that U internal equals to 1 by 2 of P into delta. So what here the delta is PL by AE. So you write PL by AE. So you got the internal work done, internal strain energy stored in the bar subjected to axial force, that equals to P square L by 2 AE. Similarly, let's say you got some beam, you got a beam. Say this was your beam. You got a beam. Then you apply some loads. Say this was your beam. You apply some loads here. There is some loading. So it deforms, say along the neutral axis we represent elastic curve as the centroid line of the member. Say it deforms in this fashion. If we take at any x, we take some strip. We say that what is the moment at any x? There is some moment x, mx. So because of that moment, we write here firstly topic that bending, internal strain energy stored because of bending. Say because of moment at x, it deforms that small dx. It deforms the small differential element dx by some amount of d theta. So if it deforms it by some amount of d theta, we say that the curvature, we know the relation that 1 by r equals to d2 y by dx2 equals to d theta by dx equals to m by ei. So if we say what is the value of d theta, that equals to in terms of moment, that equals to m by ei into dx. So in deforming the material by some amount of d theta, you need to apply a moment of m. Then we have the relation. But we know the external work done. We have that relation that external work done equals to half of m theta. If we equate that with this internal strain energy, so if we say if we say that small internal strain energy is stored in that small material, small differential element in dx, small strain energy stored in dx, that equals to that half of m into small d theta. Is it half of m d theta? Yeah. Then we have that 1 by 2 m, and the value of d theta here, if we substitute here, this one was your external strain energy stored in the material in dx. So we write that half of m into d theta, that is your m dx by ei. That equals half of m square dx by ei. So if you integrate it, if you say what is the total strain energy stored, that equals to integral 1 by 2 m square dx by ei from the value of 0 to length L. So we have a simply support beam subjected to a UDL. We have that loading symmetric, so deflection is also symmetric, and theta is 0 at the mid. Theta is 0 at the mid. Then we say that what is the value of theta at any x dash from the mid, from either of the side. We want to say what is the value of theta here. So we say that here the theta is some value of small d theta 1. That theta 1 equals to summation of all d theta in those small differential elements. This differential element, this one, up to the point that midspan, and we do the summation of those small d theta to get the final value of that theta 1. Similarly, if we say what is the value of theta at the support, we say that summation of all those small strips, they have contributed small deformation of slope d theta, and if you sum them, you can get the value of theta at the support. So finally we got the equation that internal strain energy stored in the beam because of that bending, that equals to 1 by 2 m square dx by 2 ei. So similarly we can say if you have beam, then you apply a torque. If you say what's the this one is your torsion. If you say what is that internal strain energy stored, you can say 1 by 2 t square dx by 2gj 0 to L. Similarly, for the shear, you apply shear. Say you apply for the shear force. For the shear force, you say internal strain energy stored equals to half of that shear force v square dx by 2 ag. And similarly, we have some factor also. We call it as, it's a function of shape, so we call it as a shape factor. It depends on the cross section of the material. Then we have one more, that one is your shear, then is your torsion, then is your moment, next one is your axial force. Similarly, we can write p square dx by 2ae 0 to L u internal. For the axial, you can write u axial. This one is your u axial, this one is your u shear because of the shear force, the internal strain energy, because of the torsion internal strain energy developed. So we have that these terms. We would write, say we have that ei, we have ae, we have gj, and we have ag. We call them as this one is your flexural rigidity. This is your rigidity. We call them as flexural rigidity, and this one is your axial rigidity, this one is your torsional rigidity, this one is your shear rigidity, AG. Then we have that stiffness. We know that stiffness is P by delta, and that equals to any rigidity. Say particular rigidity, particular stiffness, you want, say you want axial stiffness, you have to say axial rigidity upon the length L, AE by L, say AE by L. Now we have that, we have the concept that that superposition we said earlier, yesterday's study, that this was your beam, so the maximum deflection was at the mid, that was delta equals to 5 by 384 omega L to the power 4 by EI. So if we say that you are applying load only in the L by 2 part, so here the deformation produced, that's delta 1. If we say, now if I add, similarly if I add on the other side of the beam the same amount of load, but for the L by 2 part of the beam, so there is some delta 2. We say that if you combine the two, you will get same amount of force, because your we know that from the superposition method that when we study that P is proportional to delta, then if it is linear variation, we can add the two effects, so we can write then we can write that delta equals to twice, or we can write delta equals to delta 1 plus delta 2, and by symmetry we can say delta 1, we can say delta 1 is your delta 2 is your delta by 2. So the deflection, if you say what's the value of deflection here, you can say 1 by 2 of 5 by 384 omega L to the power 4 by EI. So we write that, we solve the question that using the principle of energy and work and energy, we solve a problem. You calculate the deflection. When a point load P is acting at the free end, you calculate the delta at free end by using these principles. We say that we have the equation that m squared dx by 2ei, m squared dx by 2ei. This one is your internal strain energy stored, and we have that external work done equals to 1 by 2 P into 1 by 2 m into theta. Uh, 1 by 2 P into theta, or we can write 1 by 2 P into delta. If you say what is the value of that bending moment at any x, we can say bending moment at any x equals to minus px. If you substitute here internal strain energy equals to that 0 to L, that value of bending moment at any x, we can write minus px whole square dx by 2 ei. Then we can write it equals to p square L cube by 3, and you have 2 ei, p square L cube by 6 ei. So if we equate it, if we want to equate it with your half of p into delta, half of p into delta, half of p into delta, so we can say delta is your p square p L cube by 3 ei. But this is that conventional method, but this approach is only valid. This approach is only valid if the delta at any location I, delta at ith location, you are finding, for that the P should be only 1. P should be only 1. There should be only one load. That should be concentrated load also. P should be only 1 on the beam. There should be no other load acting on the beam. There should be only one load acting on the beam, and that load should be at the ith location also. So this is a limitation that by using this directly, that internal work done equals to external work done. This is valid when there is a load acting at a point. Load is acting, we can say load is acting at a point. Why you want to find the deflection? Load is acting at a point. Why do you want to find deflection? Where you want to find deflection? So this is the limitation, and only we can write only one load is acting for the entire beam. So this is a limitation. To overcome the limitation, we have different methods. To overcome the effects, we have the limit. We have the methods of that. One is called as virtual work method, or we call it as sometimes unit load method also. Next one is your Castiglianos theorem. So in this strength of material, we'll be dealing a part of Castiglianos theorem. Rest of these methods we'll be dealing in the structural analysis. So a part of that Castiglianos theorem will be dealing that. So here the limitation was that we overcame the limitations of the simple strain energy equals to external work done. We say that we can have delta at any location I, but there should be at that location there should be a particular load pi, and when there are many loads also, there can be many loads also acting on the beam. So we can go to the Castiglianos theorem. So you have that Castiglianos theorem. You write Castiglianos theorem. We call it as method of least work. So the assumptions deployed here is that material is, as you know, material is linear elastic. It's showing linear elastic behavior, that P proportional to delta, stress proportional strain, this one. Then we have that the temperature is constant. Temperatures don't change, because temperatures also, by changing the temperature, there is change in that deflection also, because as you have studied that as deformation of bars by using that concept of thermal stresses. So there is deformation of bars also. So we say that temperature should be constant, and the supports should not yield. We write supports should not yield. Support should not yield, or support unyielding. Support should unyielding. Support should show unyielding. Then we have that this is a general beam, that P, and there is some loads also. So we want to say what is the delta at this point I, say that point I. We want to say what is the delta at I. We write that the Castiglianos theorem says that if you want to get the delta at I, get the total strain energy stored in the beam. Say get the total strain energy stored in the beam, then you minimize it with the load acting at that point. If you minimize the strain energy, minimize that strain energy with respect to what? With respect to load acting at that location I. Why do you want that delta I? So this is your that Castiglianos theorem. By knowing the strain energy at any location x, we know that strain energy we have that say at any x there is some moment mx. That mx moment at x is some function of load p, that load p. So it's a function of p. When it's a function of p, say what's your strain energy? Strain energy is your 0 to L, that m squared dx by 2ei, and this is you have to minimize it with your load acting at location p. location I, then we have that. And so we write that in this fashion also, that 0 to L, when you integrate, m is a function of p. When you are differentiating it, so we can get 2 into m, and internal differentiation, say dou m by dou p dx by 2 ei. And finally, if you want to say what's the delta at I location, we can write that, or we can say delta equals to 0 to L m dou m by dou p and dx by ei. We can also write it sometimes also this way, that 0 to L m by ei and small m dx. While your small m represents that partial derivative of that moment m at any x with your load p acting at that point, while you want to find the delta. So this was so this is the so actually he gave that two methods, two theorems. This is your second theorem, Castiglianos' second theorem. It says that deflection at any location I is equals to first partial derivative of strain energy with respect to load acting at that point I, or location I, and that load, it should act in the same direction. It should act and it that too it should act in the direction. It should act in that direction of desired deflection. Say we know that here there will be some deflection because of the load. There is some deflection downwards, so the deflection should be in the direction, and the load should be in the direction where deflection is to be desired. So this was your that second theorem. Similarly, if you have to get the value of that moment, theta, you can write it in terms of theta also. Say you need to get the value of theta at any location I. You say integrate the moment that function m, and you write it as that small. I write it. I would give it a notation of, say, m theta dx by ei. Why your m theta equals to dou moment at any x divided by the moment you applied at any location I. Say this was your external moment applied. This is your external moment applied at that point. This is the bending moment at any x. So you got the relation that theta equals to integral 0 to L m theta dx by ei. So these two results we'll be using to solve our problems. So let's say that and one more point is that let's say there was no load let's say there was no external load. If there is no external load p or any m acting at the point, acting at I, so the theta that delta at I or theta at I, how can you calculate then? Using this method, we say that you apply a pseudo load p or pseudo m, can write it p pseudo m pseudo at that location I. Then you get the moment at any x. Because of that, then you calculate the moment at any x. Then you substitute the value of mx in your strain energy, get the value of strain energy. Then you substitute value of p pseudo equals to 0, or if you want to find the theta, then you substitute the value of pseudo moment equals to 0. Thereby you get the value of delta at any I or theta at any I. So we'll solve that question. First problem, that say you have 10-meter beam, cantilever beam. It's saying that get the value of theta b and delta b, theta b and delta b, but the b is at a point 5 meter from your cantilever side, that fixed support. Then we have this one also 5 meter. You are applying a point load of 3 kilonewton at the free end. It's saying that get the value of theta and delta at this point. So if we solve it separately, say we want to get the value of delta. Firstly, let's say get the value of delta 1. Let's say part 1, get the value of delta b. We know that delta b can be calculated from the strain energy by using Castiglianos theorem, that moment at any x, m square dx by 2ei. Then we write it as in this fashion, that m dx by ei 0 to L. So you need to get the value of moment at any x, and you need to get the value of that partial derivative of strain energy with respect to your load at that point where you want to get the delta. So where m is your, we can write m is your that dou m by dou p at the location of b. We can write it as mb, where mb is your partial derivative of moment at any x with respect to the load applied at that location b. But the load is not applied at the location b, so we have to apply a pseudo moment, pseudo load, apply pseudo load at b, pseudo load at b. So finally you have to apply a pseudo load at b. You have already that 3 kilonewton acting here. You have to apply here a pseudo load. We can write it as p. You have to apply a pseudo load of p at b. Then now you can do that. Now you need to calculate, since you have to that two spans. If you write it as a b c, you need to get the value of moment in x in the both the spans. Let's say you take the reference from here for the span bc. If you write that for the span bcb, your moment equation at any x becomes that this is your load 3, and here you are solving that. Say there is a moment mx, so you can write that mx equals to minus 3x. So you got the equation for moment x. Then similarly you can write that moment equation for the part BA. If you write the moment equation for the part BA, the effect of that 3 kilonewton has to be also accounted in that BA, because effect of that it would be there. So let's say you're cutting just before. If you cut just before, let's say you want to say what's the value of moments here that can be transferred, that would be transferred to the point B. Say you cut a section just before point load B at B, so this is your 3 kilonewton for 5 meter acting. So here there would be some shear force of 3, and moment developed here would be say this is your clockwise, here it would be anti-clockwise 3 into 5, that's your 15 kilonewton. So your moment of 15 kilonewton meter has been developed on the that point B. So when you take the for this, if you take the x from here, for that you have to calculate now. If you write that for part B, for part or section BA, you need to show that loadings at any x. So this is your loading at any x. Here some shear force V and moment mx. So we say that here the loading, you have to show the load also, that pseudo load also. So this was your pseudo load acting P, and because of that transfer of forces, this one you have to show the forces. Here the shear force is upwards 3, here it would be downwards shear force of 3, and there was a anti-clockwise 15, here it should be clockwise 15, and this was your x. So if you say what is the value of moment at any x, you write that p plus 3 into x clockwise, and 15 is also clockwise, and moment is also clockwise. That means then you calculate it, you can get the value of moment mx equals to minus times this value. minus times this value. Yeah. So we got the value of moment at any x. Say we got the value of moment at any x in both the spans, but we need that small m. What is the value of small m? That the moment at any x you got, you differentiated with that load p. You differentiate it with your load p. So if you say what's the value of m here, you can say dou mx by dou p. That equals to 0 here because there is no p acting here in this part. So we got the value of m here 0. So what's the value of, we can write m here, that equals to dou mx by dou p. So that equals to if we say that equals to minus times x, this one. So this was your equation, that dou by dou p of minus times p x minus 3x minus 15. So you have to differentiate it with x, p with p that we can get as minus x. So finally we were having two segments, but the first segment contributed 0. So you can say that first segment contributed 0 in this equation. If you write that, now if we say what is the total delta at b, we would write that 0 to, now we have to say what is the range of x also. Range for the bc, the range was from 0 to 5. Range was 0 to 5. If you write 0 to 5, m was there minus 3x, but the value of x was 0, dx by ei, and you had to add plus. Then for the span, this part, this one, the range was from 0 to 5 meter. So you write 0 to 5, then value of moment, the value of moment was that, the value of moment is that, this is the value of moment. You write that value of moment is minus times p plus 3 x plus 15 whole negative, and this one moment at any x, you multiply it with your m. The value of m we got as minus times x, so we write minus times x. You then do dx by ei. So first part gone. Now you integrate it. This part you have to integrate it. Then now we say that since the value of p was not there, we apply a pseudo load of p. So finally we got the delta in terms of dou u by dou p. Now we say that set the value of p equals to 0. When we set the value of p equals to 0, the equation would look like delta at b equals to 0 to 5 minus times, and minus would become plus, minus and minus that become plus. So we write that. So finally it becomes 0. So your equation becomes 3x plus 15 and into x dx by ei. So you solve it. You can also solve it in your that calculator also. So you write that 3x square by 2 plus 15x 0 to 5 and by ei. So you get the value of delta at b, that comes out to be 625 by 2 ei. 625 by 2 ei. A positive value means that the deflection is delta b is in the same direction as the load, as of the load direction, as of the p direction. So we assume that load was acting p downwards. Similarly, delta is also acting downwards. So finally we got the delta at b. Now we need to get that what we say, that we need to get theta at b. So say this was your beam, and point b was here. Load was acting a load of 3 kilonewton here. Then say for the theta b, you have to, there is no load at there is no moment at theta b. For theta you need a moment m, but moment m is not applied in the problem. So here you have to apply a pseudo moment m. Let's say you applied clockwise moment of m. So apply pseudo m, pseudo moment m at b. Now you say that since your moment variation, since your moment equation in the segments vary, in this segment your moment equation varies, and in this segment your moment equation varies. Since because moment equation varies, so you write separate moment equation, separate moment equation, and you calculate separate strain energy. Then you finally add them, then you differentiate the final values, and you get the value of delta. So similarly, we can transfer the effect of 3 kilonewton in this part. So say this was your 5 meter. So if you say the free body diagram, 3 shear force 3, and a moment of, this was your 3 into 5 clockwise, this would be anti-clockwise 15. So this would be transferred to that part of that beam. Say this one. There is already acting a moment of m clockwise, and a 15 also is acting there, 15, and a shear force downwards equals to 3 kilonewton. So we say that, let's take now strips that this is your some value of x, and this is some value of x, and the range is 5 meters, 0 to 5 meters, 0 to 5 meter. Then you say, then you say what's the value of moment at any x. Say value of moment at any x. You write that m plus 15 acting in the clockwise plus 3 into x, and say moment here is mx, that's also acting anti-clockwise, so we can write moment at any x is minus times the total value of this one. So we write that what's the value of that m theta. M equals to dou mx by dou m, isn't it? M theta, or we can write m or m theta, dou mx by dou moment applied. So your moment applied is m. So if you differentiate it with your m, so we can get the value of minus 1. And in this case, if you say what is the value of that moment at any x, you can say 3 into x equals to moment at x minus times. So your m becomes 0, because there is no m external, that pseudo moment in this equation here, dou mx by dou m. So contribution here from this part becomes 0. So if you say what is the value of theta, so I can say theta equals to 0 to L. Value of moment is minus times m plus 15 plus 3x into that small m, that's minus 1, and dx by ei. Now we had to say, since there was no external moment at b, we say set m equals to 0, because you applied it as a fictitious moment or pseudo moment. Then you say the equation becomes 0 to L, that minus times 15, or we can say positive 15 plus 3x dx by ei. So we get the value of 15x plus 3x squared by 2, 0 to L. But the value of L was from 0 to 5 meter. You can write 0 to 5 meter, 0 to 5 by ei. So finally we can get theta at b equals to 112.5 by ei. So you got a positive value. That positive value of theta at b, positive value of theta means the direction you assumed that moment is acting in this direction. You applied a zero moment of in this direction. That means theta b is also acting in this direction, that clockwise moment with respect to your horizontal axis, say. So this was your final, this was your load, external load. If we say what is the deflection and theta here, this was your theta clockwise, theta b, and this was your downward deflection of delta b. So finally we got this one, that Castiglianos theorem. This one, that Castiglianos theorem, we can use it to get the value of redundant reactions also. By using the compatibility conditions, we can get the value of that theta, that redundant reactions also. If we know that compatibility condition, that unknown forces and known displacements, if we relate them, we can get the value of redundant reaction by using the Castiglianos theorem. Say you have a proper cantilever. Say if you have proper cantilever and you apply a u real of W for the entire span, here is the support B. If we say uh, get the value of theta B, here we know that compatibility, that delta at B equals to 0. This is your compatibility condition, compatibility equation or condition. Then we know that there would be some theta at B and there will be some reaction at B. We need to get the value of theta B and reaction B. Firstly, if we get the value of theta, that reaction at B, say the reaction at B is equals to B, and if we say what's the moment at any x, because there is only one span, we can say moment at any x equals to, or we can say there is no change in moment equation. We write only one equation for the entire AB span. So we write moment at any x becomes equals to that minus pb minus b into x and clockwise of wx square by 2 and moment at clockwise of mx. So we write mx opposite, so we write it as positive, then it becomes negative finally by transferring the mx. So finally we got the value of moment at any x mx. uh, we know that to make for the delta equals to dou u by dou p, that equals to integral m dx by ei. For this, we know that delta at b equals to 0. If you say what is the value of delta at b, you would say that then you have to differentiate it with a load that dou u by dou p. That load p should be acting at the point b, since already there is a reaction of b acting at that point. So we have to differentiate that strain energy with respect to your load b, your reaction b. So if you differentiate it with your load b, so there is no need to apply a pseudo load of any p, but because there is already a reaction giving provided by that support, we can say we have to minimize that strain energy with respect to your reaction at b to get the delta at b equals to 0. So finally we got the moment mx. We need that small value of m, that equals to dou mx by dou b. So value of dou b becomes equals to x plus x. So finally we can write delta b equals to 0. So if we say delta b equals to 0 equals to 0 to L, value of moment is bx minus wx square by 2, and you multiply it with your value of m, that's x, then dx by ei. After calculating it, you can get the value of that bx square by 2, that's bx cube by bl cube by 3, and you get here the value of wx cube, wx power 4, wl to the power 4 by 8 ei equals to 0. That means the reaction value, that reaction provided by support B equals to 3 by 8 of WL. Now if you say what's the value of theta at B, if you say what is the value of theta at B, for the value of theta at B, you have to apply a pseudo moment of that. We got the reaction at that 3 by 8 of WL. Now we can erase this part. Let's say for calculation of theta B, we say let's say that you apply a pseudo moment of m at B. Let's say apply a pseudo load of m at B. So we write equation at any x. Say this is your mx. What is the value of moment at any x? We write moment at any x plus that b minus times b into x. Then we have positive wx square by 2. Then you applied a clockwise moment of m. We equate it with your 0. Then we say what's the value of moment at any x mx. So that equals to b into x minus wx square by 2 and minus m. Then once you say that what is the value of m into m theta, that equals to dou mx by dou m, that is minus 1. Then we say that what is the value of theta at b, you integrate it 0 to L, value of m you substitute bx minus wx square by 2 minus m into value of m theta, that's minus 1. Then you say dx by ei. Now you say, since there was no moment m applied at that point, you say set m to 0 and the value of b equals to 3 by 8 of wl. When you substitute these values, you get the value, you get the reaction, you get the theta b equals to 0 to L, 3 by 8 of w into L, 3 by 8 of w into L and your x, and you have to multiply it with your minus times x, so we write it as minus times. Then similarly this one becomes positive, wx square by 2, and this one is 0 because m is 0. Then you have to integrate it, dx by ei. Say this is your minus 3 by 8 wl, then x dx, that is x square by 2, that's L square by 2, and here plus wl cube by 3, wl cube by 3, L cube by 3. So we get the value of theta at b. If you say what is the value of theta at b, we can calculate that. 3 by 16 minus 6 inverse, that's minus times wl to the power 3 by 48 ei. That we get the value of theta at b equals to minus wl cube by 48 ei. Minus means that the moment direction you apply, that moment applied at b is clockwise, but the theta should be there. That means theta here should be anti-clockwise. Theta negative means theta should be anti-clockwise. If you say this was your beam, then you apply load, so the deflection profile would be somewhat this one. So your theta becomes anti-clockwise theta. That's your theta anti-clockwise. Now we have one more problem. Say you got a 12 meter beam BC, and we got one more inclined member, that's AB, at an angle of 60. This is your theta equals to 60 degree, and your UDL of 2 kilonewton per meter is acting on the beam, 2 kilonewton per meter for length of 12 meter, and this is your 10 meter along the length. Say this is your A, B, and C. You need to get the value of theta at C. So for the theta at C, by using Castiglianos theorem, there is no moment applied at the C, so you apply a pseudo moment. So apply a pseudo at C. So let's apply a moment of m here. M equals to 0. So we apply a pseudo moment of m equals to 0 at the point C. Then we say that calculate the that free body diagram, make the free body diagram, and see what's the value of shear forces bending moments. Say you calculate it for 12 meter. This was your m, and this was your UDL of 2 into 12. That means here the reaction upwards should be equals to 24, and the moment here developed should be equals to, say, because of this there is clockwise, and because of this there is clockwise, so here there should be anti-clockwise moment of m plus 24 into this length, 24 into 6, 24 into 6, that's 144 kilonewton meter, and same would be transferred in the member AB. So this is member AB. Say this is vertical shear force of 24, and it has to be downwards 24, and moment it was here anti-clockwise, so here it would be clockwise moment of m plus 144. But the thing is that 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 you don't know the value of that shear force perpendicular. That's the shear force should be along the transverse axis of the member. So we have to resolve that 24 kilonewton along the axis. Say this is your theta, and you are applying a load of that 24 downwards, vertically downwards. So if you say this is theta, that means this one is also theta. This is theta, this is theta, this is 90 minus theta. So if you say what is the component along this line, that's 24 cos theta, and along this line, that's 24 sin theta. We don't worry about that 24 sin theta that is along the axis. We are worried about that the shear force created, that's 24 cos theta. That cos theta equals to that 1 by 2 cos 60 1 by 2. So we got that equals to 12 kilonewton shear force. So we can show that. So this was your member. Now you applied a load, a concentrated moment of m plus 144, and a shear force of that downwards 12 kilonewton in this part. So now you take section at any x. Say you take section at any x. Say you take at any x. You need to get the value of moment at any x. So we can write moment at any x. That's clockwise. That is minus times m plus 144, and this is clockwise, and next one is also clockwise. This one is also clockwise. So we write it as positive 12 times x. So we got the value of mx. We need to find the theta at c. So for theta, you need to differentiate it with your moment m. So m equals to dou mx by dou m. That is minus times 1. That's minus times 1. And similarly, we can make we can get the value of moment at any x in this part also. We would say what is the value of moment at any x? That's minus times, say this was your clockwise m plus wx square by 2. That's 2x square by 2. Yeah, this is your relation. That then finally we can say what is the value of m? That's dou mx by dou m. That's minus times 1. So we have the range of x is that 0 to 12, and for the AB we have range of 0 to 10. So we can finally say what is the value of that theta at c. Right, theta at c equals to 0 to 12 m. That's minus times m plus 2x square by 2. Then we have minus times 1. Then we have dx by ei, and plus 0 to 10 for the part this one. We have moment of m plus 144 plus 12x. So we write minus times m plus 144 plus 1 to into x, and you have to multiply it with minus 1. So, and the range was 0 to 10 meter dx by ei. Now we say the set value of m equals to 0. If you set value of m equals to 0, so this one becomes 0, this one becomes 0. Finally your theta c becomes 0 to 12 positive value of x square dx, x squared dx by ei, plus 0 to 10 144 plus 12x and dx by ei. And when you solve it, you get the value of theta c, that equals to theta c comes out to be equals to 112 point, no, that's 2616.9 26166 by AI. That's positive. Positive means the direction of m you applied in the clockwise, same would be theta developed at that point. Say this one. So because of this loading, there would be some deflection downwards. So the theta would be theta would be clockwise. Say we have one more. Let's say this one is your problem, that if you want to say what is the total strain energy developed in the members, say this is point A, there is a hinge support, then after that a point load of P, then after that a concentrated moment of M, then after that a preload that roller support at D. This is B, C, D. This is 1 meter, this is 2 meter, this is 4 meter. Say you want to get the U total, strain energy total. Let's say the reaction here is A, here the reaction is D. If you say what's we don't know the value of these P and M, and we don't know the value of reactions also. So to make it simpler, we can use that Macaulay's approach to get the strain energy. If you make a one moment equation for the entire section, entire beam, you cut dx just before d. You say what's the value of moment at any x. If you say value of moment at any x equals to, that's clockwise, anti-clockwise, okay, then we get the value of a into x plus then we have minus times p acting after that x minus 1. Then after that we have moment m clockwise, we write positive, but it is after m, that x minus 3, after x minus 3 it's acting. So we had also show that zero power. So then after that, for different sections, we say that, let's say you want to say what is the strain energy stored in the segment AB. You write summation that m square dx by EI by 2EI 0 to the range of AB is from 0 to B, that is 0 to 1. So but for that, in the AB, these terms we have to say whether they are valid or not. For the AB only the reaction AX is valid, so we have to say the value of m at in the AB should be equals to a square x square dx by 2EI and 0 to 1. So we can get a square, and value of x we say substitute it to 1, then we can get x cubed by 3, that's 1 cubed by 3. So we can get a square by 6EI. Similarly, if you want to say what is the strain energy stored in the part BC, you say you have the limit from that 1 meter to 3 meters. So we write 1 meter to 3 meter range. Then we say moment in the BC. So moment in the BC is contributed by two loads. One is your reaction at A, next one is your reaction that P, so point load. So the two terms would be included in the moment equation. So we can write A into x, then minus P, minus Px, minus P. Then we say that this was your moment equation. Then you do square, then you have to say dx by 2EI. Then you calculate it. Say you keep the sign, say this was your x minus 1. If you keep it as x minus 1, then you solve that. First you have to say square of this function, so it becomes that is 1 to 3 a square x square minus plus b x minus 1 whole square minus 2ab 2a and b. So finally you got this. Then you simplify this one also, that x minus 1 that's x square plus 1 square minus 2x. Then you have a square x square plus this one minus 2a ap x square, that x into x minus 1. Then you say dx by 2EI. After solving, you can get the value of strain energy in A in the part BC. Similarly, for the part CD, you can write that strain energy in the part CD equals to, in that part there would be all those all those effects that mx full momentum equation, that ax minus bx minus 1 plus mx minus 3 power 0 whole square dx by 2ei. Integral is from, after the integral is from the 3 meter to 7 meter, 3 meter to 7 meter, 3 to 7. So say now we have a beautiful problem that you have beam, this is your front view, this is your side view. Say this is length L and this is the depth D, but if you see from the top, it looks like, say it looks like this. So this is your top view, top. Say here the width is 0 and here the width is b, so it's varying from 0 to b in length L. If we say what is the 3D looks like, how the 3D looks like, you can show that. So this is a beam. If you cut at any section x, so there is a point load acting at the free end, so the load of P is acting here. If you want to say what is the value of moment at any x, then you have to say moment at any x. You can calculate moment at any x. That's easy. That point load acting here and moment at any x would be moment at any x, that equals to minus times px. That's okay. Moment at any x minus px. You want to say, the question is saying that get the value of delta maximum. The delta maximum would be at the free end, delta maximum. So for that, there should be some point load acting at the point, that free end. Since there is already acting that point load at the free end, so there is no need to apply pseudo load of P at the free end. For the delta maximum, we have the equation that for the delta maximum, we have that delta equals to m dx by ei, 0 to L. But your value of I is also changing here. It should be I into x, that I at any x, because your value of b is changing. If your value of b is changing, say at any x, you have that cross section b at any x. You need to get the value of b at any x. So this one. So this is your b at any x. Say this one. This is your bx, and this is your d. D is constant. So we say that about the neutral axis, we have the value of a ix equals to b x d d cubed by 12. But the value of b is such that value of b at any x is such that it is b at the L, but at the x it is bx by L d cubed by 12. So finally we can write that equation here. Say the value of m is also that dou m x by dou p, that's minus times x. So you substitute the values, that 0 to L minus px and minus x and dx by e into I. The I value of I was b by L into x into d cubed by 12. So we get the values that, and your x here gets cancelled. And if x gets cancelled here, say 1 1, then we can get the value of p, that value of p into x squared by 2, then you have value of e b L and b, and that bd cube, the bd cube, that's b d cube by 12. So you substitute the value of x equals to L, we can get the value of at pl cube by 2 e bd cube by 12. that's equals to PL cube by 2 EI max, yeah, delta. The value of I max is at the support where there is a fixed support. Say at the end there is this b, that b d cube, that b d cube by 12. This is your I maximum. That's equals to b d cube by 12. So you can write PL cube by 2 EI max. Let's say you take one more problem. Let's say that this is L by 2 and L by 2 and L. Here is some support at point B. You apply a load of P at A, and this is L by 2, this is L, and there is some internal hinge at H. After that there is some spring and fixed at the bottom. So the stiffness of this spring is equals to 3 EI by L cube. You need to get the value of delta. You need to get the value of delta at location A. For the delta at location A, there should be some load, concentrated load acting at that location. But there is given that P is acting, so there is no need to apply a pseudo load of P at A. So we have that already provided. So we have to make the free body diagram. If you want to make the free body diagram, this is your free body diagram looks like. So this is the free body diagram, that P. Here there would be some reaction at B, and here would be some, say, reaction here would be some Fs. If we say by the force equilibrium or moment equilibrium, say summation of moments at B equals to 0, we write P into L by 2. It is clockwise, anti-clockwise. Then we have plus Fs into L by 2. This was your L. Fs into L clockwise equals to 0. That means force in the spring that equals to P by 2, and that was here downwards, and in the spring it should be upwards. So this is your spring force. Here it should be upwards. So final diagram, final equilibrium diagram should look like that. This part going downwards and this part going upwards, such that spring gets that elongated. So this is some sort of profile it should be having. So finally we got the forces. We can say what the strain energy stored to get the deflection at point A. We say let's cut the section for this one at any x, and for this one cut the section at any x. Here we don't need to get the value of reaction at B, so we can cut the section. For this part we cut it from here, and for this part we cut it from here. If you want to cut from any of the sections, say if you want to cut if you want to take from A the value of x for this part B, C also, there is no issue. But you have to check the effect of that P and the reaction B also in this part at any x. So that takes more calculation than if you say we know that reaction at here is Fs. You only need the reaction of Fs only here, because there is no external load in this part. So there is only moment of minus times that Fs into x. So you have to be very smart in that selecting the that desired x. Let's say for the part AB, you would say moment at any x. Say this is a moment at any x, mx. We write you say that P is acting clockwise, anti-clockwise, and moment is also acting anti-clockwise. So finally it transfers. Finally you get the value of mx equals to minus px. Okay. Then after that you say what is the value of m? That equals to minus times x, that dou mx by dou p, and range from 0 to L by 2. Now we take part BC. In the part BC, you say the value of moment at any x. That's say fx into x, fs into x, and you got a moment of clockwise moment of mx equals to 0. So your moment at any x becomes equals to minus times fx minus times fx. Value of fs becomes p by 2. So now we say that what is the value of m? We write value of m is minus x by 2, and the range is 0 to l. 0 to l is your range. Let's take that now. What get the value of delta b, delta at a. So delta at a, that's integral 0 to, in this part, 0 to l by 2, 0 to l by 2, and you don't have to set p equals to 0 because p is already acting there. So you have to keep the p as it is. So we write minus p into x and into minus x, then dx by ei, then plus 0 to l, 0 to l, 0 to l. You have the moment equation that 0 to l, that minus p by 2 of x, minus p by 2 of x, and your small m of minus x by 2, dx by ei. And we have to see also that contribution made by the spring also. Say the spring, say the load was gradually applied. Say the load was gradually applied from 0 to p at location A. Now say the force developed in the spring is develops from 0 to some value of final value of p by 2. So if we say plot that, say at fs equals to p by 2, you got some value of delta elongation in the spring. Delta elongation in the spring, we say that strain energy stored in the spring is half of p into delta, and your value of, and you have to say what is the value of p here. Value of p should be equals to, this value is p by 2 and delta 1 by 2 p by 2, and delta value is, we know that delta is equals to that p by k. So if you say but the value of p here, p applied in the force, we can say fs by k. Actually we can write fs by k. So we can write fs value is p by 2 and fs by k. So we get value of strain energy p square by 8k, p square by 8k, p square by 8k. Then you substitute the value of strain energy in the spring also, that p square by 8k, and this was your strain energy stored. This was your strain energy stored. How can you get it in terms of deflection? Say you need delta A, but it is a strain energy value. If it is a strain energy value, we have that relation that delta equals to dou u by dou p. So you can write it as dou by dou p of strain energy, because of axial, this is because of spring strain energy stored in the spring. So that we call, if we say what is the value, say minus, that becomes plus px square, then it becomes px cube by 3, then the value of L, we can write px cube by 3 and divide by 3 ei, plus then we have that. Similarly we can write px square by 4, then it becomes px l cube, px cube by 3, px cube by 3, then we have 4 ei. Similarly we have that p square by, or we can write p by 4k, then you solve this one, it becomes 8 inverse 24 inverse plus 12 inverse. Is it pl cube, is it pl cube by 8 ei plus p by 4k, pl cube by 8 ei. Px cube by 3 ei, px cube. by 3 EI. You just check it. You just check the value. See whether it comes out to be equals to some value of 5 by 24 PLQ by EI. Just verify it. Maybe you can calculate it. It's not a big deal. Let's move on. Let's move on to the next one. Now we have a beam that's in the form of quarter of a circle. So we got a quarter circle beam. So this is your the range is that the theta value of theta is from 0 to pi by 2. So this is your center O. Then the theta is from 0 to pi by 2. So this is called as quarter circle beam. Quarter circle beam. Now you have applied a load. You have applied a load of vertical load of P at the free end, and you need to get the value of delta. Say this is your point B, this is point A. You need to get the value of theta at B, and you need to get the value of delta at B in horizontal direction and delta at B in vertical direction. So we can write it as delta horizontal and delta vertical at B. So for that, for delta vertical, you already have applied a zero load of B downwards. For your delta horizontal, you have to apply a zero load of, say, H. H is your pseudo. So problem was just that a quarter circle beam having a load of P. So by using Castiglianos theorem, you have to apply a pseudo load of H for getting the horizontal displacement of point B. Let's say this is a radius R. This is also radius R. This is also radius R. Now, if you say whenever there is an arc beam kind of thing, that in terms of x, in terms of dx and x, it becomes difficult to solve, and moment equation becomes difficult in terms of x. If you take in terms of theta, it becomes easier. Take in terms of theta, so the function becomes easier. So if you take a strip at theta from with respect to point B, say you take a theta, you take a strip. Say this is your strip, making d theta. This is your radius R. Say this both are radius R. Say this is radius R. Then this one is your some value of d along the surface, that equals to r times d theta. R times d theta. Then we have that we want to say what is the value of moments at that particular theta. Say this is your theta. Say this one is your theta. This is theta. We want to say at theta, get the value of moment m theta. What is the value of theta at? What's the value of moments at particular theta? So we want to say, let's cut the section at theta. So if you cut the section at theta, say here the shear force is V and moment here is m theta. Then you have applied a load of P downwards P and a horizontal H. So we want to say what is the horizontal distance of this one and vertical displacement of this one. So then we can do that summation of moments about the point at theta. So for that you have to see that is there any triangle formed. Say if you say this one, we have a triangle, right angle triangle. If this is R horizontal, this hypotenuse is R, this is theta, then this one is R cos theta, this becomes R sin theta. Isn't it? R sin theta or cos theta, and the value of this one, this is R, total was R, you have to subtract it by R minus R cos theta, R minus R cos theta. So this one you got as R minus R cos theta, and this one is your R sin theta. then you say what's the value of moment at any x. So we can write moment at any x, that's moment at any theta, that's clockwise, that equals to minus times that p into r sine theta, and that's also horizontal one, h into r 1 minus cos theta. So but we need two deflections. One is your deflection in horizontal direction, we can write, so we can accordingly get m, we can write m horizontal. If you want to say m horizontal, that's m dou m theta by dou horizontal, so we can get that value as minus times r 1 minus cos theta. And if you want to say what's the value of m vertical, that's dou m theta by dou p, that's minus r sine theta. So finally we got these results. We know that relation, that theta equals to 0 to L, but here we are focusing on the theta, so we write 0 to pi by 2 m theta, small m d theta, and we have to write here along the surface dx. We don't have to write the dx, we have to write along the surface ds by 2 by ei. So we have this relation m small m dx by ei, but here dx is not to be taken. We would take along the strip, along the surface, that's ds equals r d theta. So we have to substitute the now values of these, say for your theta. We don't have to get the value of theta actually. This one is your delta, this one is your delta, this was delta. Let's say you want to say what's the value of delta horizontal, delta horizontal, that equals to 0 to pi by 2, 0 to pi by 2, value of moment at theta, this one, that equals to minus p r sine theta plus h r 1 minus cos theta. This one is your, and you have to multiply it with your m in mh, small mh, that one, small mh, that's small mh is equals to minus r 1 minus cos theta, and divided by ei, and you have to multiply it with ds, that ds equals to r d theta, your ds equals to r d theta. Now for the horizontal, there was no horizontal load acting in the horizontal direction, so we have to set h equals to 0. If you say h equals to, if you set value of h equals to 0, you can get the relation that 0 to pi by 2 minus this one becomes 0, this one becomes 0, so finally you are left with minus times minus, it becomes plus, so that's p. R is how much times? R is 1 and 1, so it becomes pr cube sine theta 1 minus cos theta d theta by ei, so that equals to pr cube by ei, and 0 to pi by 2 sine theta minus sine theta cos theta, and d theta. You know that 2 sine theta, that sine 2 theta equals to y sine theta cos theta, so we have that result. We can use that. Let's say that this is pr cube by ei, and integral what is the value of sine theta, integral sine, that is minus cos theta 0 to pi by 2, and for this part, that's minus times that's sine 2 theta by 2, and sine theta by 2, that's minus times cos 2 theta by 2. So we can write that for the first time, we can write minus times that sine 2 theta by 2, integral 0 to pi by 2 d theta. So we can write pr cube by ei, what's the value of cos pi by 2, that is 0, and cos 0 is minus 1, finally minus 1. You got cos 0 is 1, that's minus 1 final. Then after that you have minus then the value of sine 2 theta it becomes minus cos 2 theta, and we have already that 1 by 2 up the we can keep it aside. Then you have divided by 2. Then we have that limits 0 to pi by 2 cos 2 theta by 2. Yeah. Then you substitute the values of theta equals to pi by 2, that is minus 1 by 2 minus times that finally becomes positive. We can write cos 2 into pi by 2 divided by 2 minus cos of 0 divided by 2. That becomes cos of pi becomes minus 1 and minus 1 by 4 and minus 1. Finally you get the value that horizontal delta horizontal is PR cube by 2 EI. PR cube by 2 EI minus 1 cos theta minus 1 minus 1. Yeah, this one was actually the value of here. This one was actually a positive one because minus times cos of pi by 2 was 0, but minus this was your minus times of minus 1, so it became positive 1 plus 2. You got the value as PR cube by 2 EI. Yeah, PR cube by 2 EI. Final horizontal displacement at point B. So you got that horizontal displacement. So for the vertical displacement, you have to now calculate for the vertical displacement. Say, if you want to say what is the value of that delta vertical, that's 0 to pi by 2. Value of moment was minus PR sine theta, and now we would directly set h to 0. If you directly set a horizontal to 0, that means this is gone, that is 0. That means you are left with this part only, and you have to multiply it with this one minus r sine theta, and value of ds was r d theta by EI. If you calculate it, you can get the value that PR cube sine square theta by EI integral 0 to pi by 2 d theta. We have that sine square theta. Equals to 1 minus cos 2 theta by 2. Then you substitute the value here. We can get the value of PR cube by EI, and sine theta, so that equals to 1 by 2. We can keep 1 by 2 common outside. Then you have value of 1 minus cos 2 theta and d theta integral. So you can solve that, and you can get the value of PR cube by 2 EI, and value of theta, that's 1 into d theta, that's theta, that's pi by 2 minus 0, and minus times cos 2 theta is your sine 2 theta, sine 2 theta by 2. Then you substitute the value of theta equals to pi by 2, and similarly minus sine 2 theta by 2. So you get the value of PR cube by 4 EI into pi. Is it so? Yeah, pi by 4 PR cube by EI, delta vertical. Now we got these. We have 2 more problems, 4 problems. Let's say you got this beam, roller at C, hinge at A, and B. You need to get the value of horizontal, that delta and theta at B, slope and deflection at B. but there's no load acting at the point B. There's no load acting at the point B. We have to get the value of that point, that theta at B and delta at B. So if we calculate for the delta at B, we have to substitute the value of, so which implies we have to set P and M pseudo at B. So for delta, we can say, let's say you have applied a delta here. Let's say this is your load, point load P. So we can say this was your loading, actual loading of 6 into 2. This was your actual loading, that's 6 kilonewton per meter for length of 2 meter. This one was your 2 meter, and we have to get the that delta at B and theta at B. So now we have applied that point load at B to get the delta at B. We can write delta at B. For that, we have applied a point load at B. Now let's say the reaction here is A, and you take this strip for the AB in this side, and for this part you take this strip in this side, and you need to get the value of theta, that reaction at A and reaction at C. Let's say reaction at A and reaction at C is A and C. We can write A plus C equals to P plus 12. Then you do summation of moments at, let's say, A at C equals to 0. We can write A into 4 minus P into 2, then 6 into 12 into 1 equals to 0. That means A equals to 3 plus P by 2. That means C equals to 9 plus P by 2. So your moment equation becomes, for AB, your moment equation becomes that, let's say this is moment at any x. So moment equation becomes that, that becomes A into x, only A into x. That means 3 plus P by 2 into x. What's the value of M? We can get the value of M, that's x by 2. X by 2. And similarly for the part CB, for the part CB, you have moment equation. Say this is your moment mx. We can write that it is clockwise. Then you can write minus times your anti-clockwise moment of C. That's 9 plus P by 2 for length of x. Then you have positive wx square by 2, 6x square by 2. So we write what's the value of M here? That is with respect to differentiate mx with respect to P. Then you can get the value of minus times x by 2 also here. In the first part you got x by 2, here you got minus x by 2. Is it actually, if you calculate, you see that moment equation becomes m by 4. Actually the reaction is m by 4 plus 9. M by 4 plus 9. M by 4 plus 9. If you see here, if you say, yeah, we have not applied the moment here till now. If you see that P by 2 plus 9x, P by 2 plus 9x, P by 2 plus 9, and P by 2 plus 3x. It's correct. We can go on. Let's say that we have solved it. Now we want to say what's the value of delta at B. For that, we have also read the range. Range is same for the both segments, that's 0 to 2, and for this one also 0 to 2 meter. So we can say the delta B equals to 0 to 2 and 3 plus P by 2 of x into x by 2 dx by EI plus 0 to 2, and we can directly set the value of P equals to 0. Set P equals to 0. If you set P equals to 0, then this becomes 0. So we can write 0 to 2 minus times 9x plus 3x square into minus x by 2 dx by ei. Now you solve these two, you can get the value of theta b. That's 3x by 2 3x by 2 plus 3x by 2, that's it, and dx by ei plus 0 to 2 minus, that's 9x squared by 2, that's positive 9x squared by 2 plus positive value of 3x squared by 2, that's 3x cubed by 3x cubed by 2 dx by ei. And you solve it, you get the value of that 3x squared by 2, that 3x squared by 4 ei plus 9x cubed by 3 ei, 9x cubed, 9x cubed by 3 ei plus 3, and then you have x power 4. X power 4 is 2 power 4 by 4 ei. Then you get the value of delta final at b. Similarly, if you want to say what is the value of theta at b, so since there is no load, since there is no concentrated load acting at the point b, so you can apply concentrated load of concentrated point load of m at b. So you apply concentrated moment of m at b. So you applied a concentrated moment of m at b. Now you are calculating the reactions. Now let's say you can write a plus b equals to 12, a plus c equals to 12. Now a plus c equals to 12. Now moment of summation of moments at c equals to 0. You can write a into 4, then this one is 0. Then after that, this was your clockwise a into 4, and this is also clockwise plus m, then minus 12 equals to 0. That means your reaction at a becomes that 12 by 4, that's 3 plus 3 minus p by 2, 3 minus m by 4, that is 3 minus m by 4, 3 minus m by 4, and this one is your 9 plus m by 4. So we got the reactions. We can get the moment equation now. So we can get the value of moment at any x, mx. So that is equals to 3 minus m by 4 of x, and there is no external load in this part also. So we can get this is the equation, total equation, that this is the total equation for mx. And if you want to say what is the value of m, we write that dou mx by dou m, that's minus x by 4. And for this part, if you want to say what is the value of moment at any x, for this part, moment at any x, that's a moment, that moment is clockwise. That means that's minus times, you can do it by yourself also, minus times, then you have that reaction c, then reaction c of 9 plus that 9 plus then we can write that moment at any x equals to minus 9 plus m by 4. This is your the reaction c. This is your reaction c. You multiply it with x. Then after that you had one more thing, that's that UDL, that UDL is clockwise, plus that's 6x squared by 2, that's clockwise. What's happening to this board? 6x squared by 2. See, moment at any x, say moment at any x, we have to solve it. We say that this one is your anti-clockwise moment. That's anti-clockwise moment. If we solve it, again, so to make the confusion clear, say summation of moments at x equals to 0. So we write that minus times c is acting upwards, 9 plus m by 4 into x. Then we have clockwise moment of that 6 into x square by 2, 6 into x square, 6 into x square by 2. Then we have yeah, that's it. You have that. Then you say that the clockwise moment is there mx, then plus mx equals to 0. When you substitute it up in the opposite side, you can say minus times mx, minus times mx. You can say mx is minus times the total value of this one. So finally you got the moment equation. Say now you want to say what is the value of m? That's m dou mx by dou m. So that becomes minus times or positive x by 4, positive x by 4, positive x by 4. In the first part you got a small m of minus x by 4. In this part you got a m of plus x by 4. And now you have to use that equation. You can use that equation that you can use that equation. Let's use that relation that OMG. Let's use that relation. We can say we can solve that. Say theta at b equals to 0 to 2, moment of m3 minus, and we can directly substitute now. Value of m goes to 0, set m equals to 0. To avoid the calculation, we can say m goes to 0, m goes to 0. So finally we can write 3 into x, this one 3 into x into small m. Small m is your x by 4 minus x by 4. 3 into x into minus x by 4 and dx by ei. And in this part you write 0 to 2. You write 0 to 2. Then you have that this one and this one. It becomes positive 9x, positive 9x, and this one becomes minus 3x square, 3x square. And you multiply it with small m. That's x by 4, x by 4 dx by ei. So you have to solve the values, you have to integrate it, and you can get the value of theta b that equals to 1 by ei. Now similar on the similar basis, we can say we can have one more problem. Say this is that you got a cantilever beam, subjected to UDL of W for the entire span W for L, and you are applied a concentrated moment also M, and you need to get the value of theta max and delta max. For delta max and theta max, we know that these would be at the location of free end. At the free end, the theta max would be there and delta max is there. So for the theta max, we have already applied a moment. This was given. So for the delta max, you need to apply a pseudo load of P. This is your P pseudo to get the delta max. So we can write a moment equation at any x. So this is your moment at any x. So we can write moment at any x. This is your clockwise plus m is also clockwise plus ps. We can write ps. We can keep it as p. P into x is also clockwise. Then your loading intensity is also clockwise. That wx square by 2. All of these effects are in the clockwise direction. Wx square by 2. So this question I would be solving directly. That I would be writing that one equation for both those theta and m. Then I substitute the value of that m and p accordingly. So this would make the calculations easier and smarter. So let's say we got the value of moment equation. So we can get the value of moment at any x. So we can get the value of moment at any x, that equals to minus times whole this value. So finally we got the moment at any x equals to this equation. Then we can say what is the value of for the theta. For the theta we write m theta. What is the value of m theta? That's dou mx by dou m. That equals to -1. Yeah, -1. And for the delta we write m delta. That equals dou mx by dou p. That dou p equals to that this part it would be if contributed here. So we write minus px differentiation of minus px with respect to p, that's minus x. And we say what's the value of delta max. We can write the value of delta max is 0 to L integral. Now we can directly say set p equals to 0. If we say set p equals to 0, then we can say 0 to L minus times m plus wx square by 2 and dx by ei. Now you can solve it, and we can get the value of delta maximum. That's m dx is ml. So we can keep the minus up outside. We can write minus then after that ml by ei plus wx square by 2. That's wx cube by 3. That's wx cube by 3. I forgot the value of that small m. Yeah, this value I forgot. So this is minus x, you have to multiply it. So this was your m into small m. So this one you have to remove. You say m into small m dx by ei. Yeah, let's solve now. We can write, say this was your m by ei. Then you had minus. So finally the value becomes positive. Finally the overall value becomes positive. This minus and minus becomes positive. So we can write minus mx plus wx cube by 2, then dx by ei, and integral it from 0 to L. So we can write ml square by 2 ei plus wl to the power 4 by 8 ei. So this is the general standard result. We already know that if you had a UDL, then the maximum deflection is wl power 4 by 8 ei, and because of the concentrated moment, it's ml by 2 ei, ml square by 2 ei. Now we want to say what is the value of theta maximum. For the value of theta maximum, we can say we had the equation theta maximum. We can write theta maximum. So in this we have to set the value of ps equal to 0, because ps was not there. We have applied zero moment. This was only used for calculation of delta. It was not used for calculation of theta, and we have to substitute its value equals to 0. So finally we get the value of theta maximum equals to 0 to L minus times m plus wx square by 2 into value of that m theta, that's -1, and that dx by ei. So finally we got this result. Then we can get the value of that's 0 to L, that's m into L by ei plus, then finally you can calculate it and you get the value of that ml by ei plus wl to the power 3 by 6 ei. These are the standard results of that that we know from the superposition and other methods we use it. So this is the end of that our class that we solved that Castiglianos method, Castiglianos theorem. And so these methods are based on the fact that so you are having doubling integration, you are having Macaulay, and you are having that Castiglianos theorem. So in these methods you are solving by, say, you are taking at any strip mx, then you substitute it in the equation. In the first two equations, you said that d theta by dx equals to m by ei. Then you integrate it twice and you solve that. And in the Castiglianos, you solved mx and you calculate it in the strain energy. Thereby, you can get the delta and theta. Now, after that, there will be some two more methods that we called as moment area method, and next one is your conjugate beam method. These two methods would be dealing based on the BMD. You have to draw the BMD first, then after that you can get the value of delta and theta. Oh, this was the end of your class. So I hope you understood the problems